So welcome. Let's have a look at rotational motion. We've done circular motion in the past. So what's rotational motion? Rotational motion is when things are rolling, revolving, that kind of thing. So let's have an overview look of it, and then we'll come back and look at some things. We're going to talk in terms of angular displacement, angular velocity, and angular acceleration. I'm going to try and link for you angular qualities with translational qualities. We're going to get started and talk about torque. Torque is the angular equivalent of force. And we'll talk about moment of inertia. And moment of inertia is the angular equivalent of mass. Now, it might seem weird that you have an angular equivalent of mass. After all, mass is mass. But when we get in lab today, you're actually going to try some of these things. And what you'll see is that you can physically feel the difference when you're rotating between when you have your arms out and when you have your arms in. It's a physical difference. The significance of the mass of your hands is much more significant when they're outstretched from the turning axis than when they're close in. So it makes a real physical difference. So although mass is mass, the turning effect of mass depends upon where it is. And then we'll talk about rotational kinetic energy, and we'll talk about eventually a thing called rolling motion. There's another integration in this, and I'll just, when I get to it, I'll just see what I feel about it, and we'll see how we're doing. I don't want to rush through this section, but I don't want to leave a whole bunch of it undone. So the first thing to realize is that there are advantages in using rotational measures for doing rotational phenomenon. I have a particle going round a circle. I could talk about its tangential speed. I could talk about its tangential acceleration. And sometimes I do. But it turns out if I talk about its rotational speed, if I talk about its rotational acceleration, math gets simpler. Life gets simpler, basically. What is rotational speed? Well, speed is distance traveled over the time taken. If I want to be vectorial, it would be the displacement over the time taken. Angular speed is the angle turned through over the time taken. So you might say, let's measure it in degrees per second rather than meters per second. Let's talk about degrees per second. Yeah, that's way to go. Angular acceleration, well, not meters per second, but degrees per second, and so on. Angular displacement, final angle minus initial angle. So I'm beginning to see a pattern where I use an angle instead of a measure of length. That's pretty much what we're going to do. We're going to get the angular equivalent for length is, it turns out it's going to be an angle. We'll talk about the units in a minute. There's the angular equivalent of mass, which is moment of inertia. There's the angular equivalent of acceleration, which is angular acceleration. There's the angular equivalent of force, which is torque. There's the angular equivalent of kinetic energy, which is rotational kinetic energy or angular kinetic energy. There's just equivalents. Whatever you've done in linear, you can do in angular terms now, because the same principles hold. So part of what we do is translations rather than learning new stuff. There is a wrinkle, and the wrinkle is that we have degrees because of our historical tradition. And it's a weird historical tradition. It turns out that in basically northern Syria, going through the Middle East, the Fertile Crescent, the Babylonians, I think it was, had a hexadecimal counting system when people in Britain weren't counting. These folks had a hexadecimal counting system 4,000, 5,000 years ago, something like that. Maybe 3, I can't remember. And basically what they did was, because it's hexadecimal, basically base 6 kind of thing. So they tended to be really good at measuring the angles between things, because they had a really fine measuring scale. And if you're dividing things up into 6s, you tend to go for 6 or 12 or 18 or 24. And, you know, hey, look what happened to us. We have 12 hours on a clock, 24 hours in a day, 12 months in a year, and we have 360 degrees in a circle. And it's completely, those divisions, a day is as long as a day. That period of time is set, but dividing it up into something that's divisible by 6 is just historical. We like decimals. There was a move actually to make 10 months in the year. There's still a move actually. People still do sometimes push for it. But it's unlikely to get traction, because actually when you try to divide things up, like 12 months means that I can charge you rent once a year, once every 12 months. I can charge you rent 6 times a year, once every 2 months. I can charge you rent 4 times a year, once every 3 months. I can charge you rent 3 times a year, once every 4 months. I can charge you rent twice a year, once every 6 months. I can charge you rent 12 times a year, once a month. Lots of divisions. Try doing that with 10. You get 1 and 10, 2 and 5, 5 and 2, 10 and 1. There's not so many divisions. So it actually turns out it's historical, but by happenstance, it's actually not a bad way of dividing. Try and divide a cake up into 10 equal slices. Oh man, the kids will be on you so badly. It's just really hard. 12 is a piece of cake. Space aliens come in, wouldn't have a clue about what a degree is, because they don't have our historical history. But they would know what a radian is. And so do we. We might call it different things, but so do we. So we say that our angle, so we've got to be clear here. So I found this confusing when I was a student. Again, it was down to definitions. So that is my angle. And I'm going to define my angle in radians. And what I do is I take my arc length, that's the distance around the circumference, divide it by the radius. And if it comes out to be 1, that's 1 radian. If it comes out to be 2, it's 2 radians. If it comes out to be 3, it's 3 radians. The problem is, the uncomfortable bit is that there are 2 pi r meters in a full circle, and you divide that by the radius, and you get 2 pi radians per circle, which is 6.3 something radians in 1 circle. And people just feel very uncomfortable with that. It's not a whole number. So call it 6. You know, in your head, just call it 6. It's no big deal. You have 360 degrees. You got 6 radians about. It's a bit more, who cares? But it's a very natural unit, and aliens will know about a radian, but they will not know about degree. So it's useful. Angular displacement, delta. Sorry about this. It didn't come out on this. So delta theta equals theta final minus theta initial. We've been there before. We said delta x is equal to x final minus x initial. Angular speed, well, we said v equal the limit as delta t went to 0 of delta x over delta t, which became dx by dt. Well, here we're going to say that omega, well, there's a problem. Omega is equal to the limit as delta t goes to 0 of delta theta by delta t, which equals d theta by dt. So now I have omega, omega, whatever you want to call it, omega. It's velocity, angvel, curly w. Okay, it's just we ran out of Arabic letters and now we're on Greek letters. You know, it's the way it goes. No big deal. Angular acceleration, well, linear acceleration was acceleration equal dv by dt, which equal d2x by dt squared. And what we say for that is that the alpha, it's just the Greek a, alpha is equal to the limit, delta t goes to 0 of delta omega by delta t, which is d omega by dt. And this is omega and this is alpha. And that is theta, you know theta. It's not a different symbol for the radian in terms of writing down an angle, call it whatever you like, but the units are RAD, radian. What are the dimensions of a degree? We write down degree, but what's that in basic dimensions? Who knows, yeah? Let's get some insight. What are the dimensions for the radian? The radian is equal to the distance traveled round the arc divided by the distance of the radius. What dimensions is a length divided by a length? Not a trick question, it's just what is it? L divided by L is 1, I guess, which is dimensionless. No dimensions. There's no dimensions for radians. There's no dimensions for degrees. There are units. We can have units without dimensions, and that catches people out. But it's a ratio. It's a ratio of lengths. Yeah. Question or comment? No? Okay. So every point on a rotating object has the same angular speed. So here's the gorgeous thing about this. If I take the same rotating disk and I take points on the radius and I say, well, look, they've gone through a certain angular displacement and it took them a certain time. So every point on that radius has the same angular displacement after the same amount of time, which means it has the same amount of angular speed. And if it's speeding up, it has the same amount of angular acceleration. Whereas you do the same thing for a linear frame, well, that's got a big tangential velocity or tangential speed. That's got a smaller tangential speed. That's got a smaller tangential speed. That's got a smaller tangential speed. So they've all got different tangential speeds. That means they've all got different tangential displacements. They've all got different tangential speeds. If it's speeding up or slowing down, they've all got different tangential accelerations. In linear terms, describing the motion of a wheel is incredibly complicated. In angular terms, every point on that rigid wheel has the same values of displacement, angular displacement, angular velocity, angular acceleration. It makes life so much simpler. So I've hinted at this before, but I want to kind of give you the idea. So before in linear we had coordinate which was measured in x, and now we have angular coordinate which is measured in radians, and we had linear displacement which was measured in meters, and now we have an angular displacement which is measured in radians, and we had a linear velocity which was measured in meters per second, and now we have angular velocity which is radians per second, and we had linear acceleration which is meters per second squared, and now we have angular acceleration which is in radians per second squared. It's all the same stuff. And what's even nicer is our VF equals VI plus AT, which you learned today, which you learned for today, is equal to omega F equals omega I plus alpha delta T. It's the same equation, it's just in angular terms. Delta X equals VI delta T plus a half A delta T squared. Well, delta theta equals omega I delta T plus a half alpha delta T squared. Oh man, 4 more equations to learn. Absolutely not. It's the same equation, just learn the translations. It's like it's a piece of cake. So everything like that is translation. A student runs 40 meters around a circular track. So here's my circular track, and here's my student, and they run 40 meters. So that's 40 meters. And this is a 50-meter track. So what is angular displacement? Well, if I'm assuming that that's 0 radians, and this is theta final, if you like, I can say my theta final is equal to the arc length over the radius, which equals 40 over 50, which equals 0.8 radians. It's positive because I'm going in a counterclockwise direction. We'll get to that in a bit. Just like we have positive number line, negative number line, we need to have a positive rotation and a negative rotation because they're opposite. Counterclockwise is positive. A point on a cylinder has an angular velocity. Here's my point on my cylinder. It's got angular velocity, that's an omega, equal to plus 3 radians per second at time t equals 2 seconds. Oh, I know what I'm doing here. And it has an angular acceleration. Let's do that. And that's going to be, let me draw that better. That's going to go in that direction. No. I will get my head together in a second. I want to get my directions right. It doesn't matter as long as they're opposite, but I'd like to get them right. This is a positive velocity, so that's going to be in that direction. And for my alpha, it's a negative, and that's going to be minus 5 radians per second squared. And what is the point's velocity at t is equal to 6 seconds, and this is my omega final. So I've laid it out. This is like I have a certain velocity, and I have a certain acceleration, and I want to know my velocity at a certain time later. It's the same problem. If we did this in linear, you'd say, why are we doing this again? It's the same problem. So what I say is, let's make a list. So omega I is equal to plus 3 radians per second, and alpha is equal to minus 5 radians per second squared. And my delta t is equal to t final minus t initial, which equals 6 minus 2, which equals 4 seconds. I was leaving a trap for people there. See if they could catch that. And then what else? Omega F is what I want to find. And this is like VI, and that is like A, and that is like delta T, and that is like VF. And I know that VF is equal to VI plus A delta T. So I know that omega F is equal to omega I plus alpha times delta T. So I know that omega F is equal to omega I is plus 3. Plus A is minus 5 times delta T is 4. So omega F is equal to plus 3, added to minus 20, so omega f is equal to minus 17 radians per second. So what you can imagine happened is in your velocity graph you went forwards and you stopped and you come back again. And in this case you rotated counterclockwise and you stopped and you rotated clockwise again, because that's a negative velocity, so you must be going in a clockwise direction. And you can see that because if my velocity is positive and my acceleration is negative, I'm slowing down. All of that you learned is applied again. All you got to do is do the translation, and it just works. So expect some kind of, it's a good way of me checking on your what's-its. It's a good way for me to check on your kinematic equations again. So expect something from there. We said that theta is equal to S over R. So let's rearrange it and say my arc length is equal to theta times R. And if I'm going to tell you it, my tangential velocity is equal to omega R, and my tangential acceleration is equal to alpha R. So my tangential velocity Vt and my tangential acceleration At, I can relate to my angular alpha and my omega, my alpha and my omega. I can relate them. And the way you remember it is angular. That's why I remember it. Angular. Take the angular bit and put an R at the end of it. Angular. I lived in Boston for a while, and they wouldn't say linear, they'd say linear. Linear doesn't have an R at the end, but angular does. Or you can remember that and then use your analogy. You know, analogies work great. We learned that AC equals V squared over R. Well, hold on. V is equal to omega R. That's going to be omega R squared over R, which gives us omega squared R. So just another expression for the circular motion stuff. It's all just translation. Point that is 5 meters from the turning axis. On a rigid cylinder has a angular velocity omega equals 3 radians per second. What's its tangential speed? What is its Vt? Oh, theta equals S over R, so S is equal to theta R. Oh, I remember. And Vt is equal to omega R. And I remember At is equal to alpha R, angular. So I want to let those two. So Vt is equal to omega R. So Vt is equal to 3 times 5, which equals 15 meters per second. Angular. Works out nicely. Rigid cylinder spins around the turning axis that passes through its center. A point located 3 meters has a tangential speed of 6 meters per second. What is the tangential speed of a point located at 4 meters? I need an equation. I need something to be constant during rotation. That's to do with this. All points on a rigid disk have the same angular displacement, angular velocity, angular acceleration. It's angular velocity I'm concerned about here, isn't it? So the angular velocity of A is equal to the angular velocity of point B. Let's call this A and that point B. And my angular velocity of A is my tangential velocity of A, angular, over my radius of A. And this equals my tangential velocity of B over my radius of B. So then that means that Vt over 4 is equal to 6 over 3. So Vt is equal to 6 times 4 over 3, which equals 6 meters per second. No, that's not right. 6 4s are 24, 8 meters per second. And don't that kind of make sense? If you plot a graph of this, 1, 2, 3, 4. I know at 0, in the middle of my circle, I got no tangential velocity. As I go out, at 3, I had a value of 6. And at 4, I had a value of 8. Oh, I get it. 2, 4, 6, 8. I bet at 2 it would be 4. I bet at 1 it would be 2, because that's a straight line graph. Your tangential velocity increases linearly with radius on a rotating disk. I remember reading a science fiction book when I was a kid, and they had this brilliant idea about having moving sidewalks that traveled at 70 miles an hour. Now, there's a bit of problem with wind resistance there, but, you know, call it 30 miles an hour then, whatever you like. And what they did was, you can't just step on a moving sidewalk that's going at 30 miles an hour, because it's like your feet get hit by a car going at 30 miles an hour. It's not going to work. So this brilliant idea where they had these big turntables and a little circular spiral staircase in between. So you come up the spiral staircase, and then you step out onto this, and it's only going at about 1 meter per second, because it's in the inside. The tangential speed is slow. And then you walk to the outside. Well, you actually walking to the outside, you're actually going to go around and round and round and round and round and round. So you get to the outside, and now you're doing 30 miles an hour. And then you step onto your 30 miles an hour walking. So you go faster, 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 faster. You get to whoosh, and then you get off at the other end. Yeah, that's there's a whole bunch of problems with it, but there's some good physics there as well, you know. I remember they invented the vacuum tube, the vacuum underground system. It was supposed to connect Boston with New York and Washington, D.C. And it reduced travel times to a couple of hours to go from Boston to Washington, D.C. They had designs for it. They had schedules for it. The idea was you have a tube that's basically a whole bunch of sections of piping. Your tube train is exactly the dimensions for the tube. You pump in front of the tube. It pulls the train forward. There's no engine. It just pulls the train forward. The vacuum does it. When you get past, you let air in. Well, bad Bonaquisti there. Vacuums don't pull. When you put the air in behind, it pushes. So kind of like, you know. The train occupies the space created by the vacuum. Air pressure pushes from behind. You go faster and faster and faster. There's no air resistance to this because you're evacuating the place in front of it. I remember seeing that. I used to teach vacuum science when I was in business. I used to teach vacuum science. And this was a little light relief I'd show to the customers and say, you know, look at this. What a crazy idea, you know. They even had schedules and all this kind of stuff and all that. And then along comes Elon Musk, who's basically doing it in California. That's his basic idea behind this exotrain thing. He'll get it to work. He'll get it to work. That guy's driven. So when you read things in science fiction, sometimes the stuff that's... I remember reading this thing in science fiction where the guy went to the library and he took out his pen and he scanned it over the book, and he had the electronic version of his paper. He went home, plugged it in, and on his viewing screen he could see the electronic version. And I was at a stage where I would be basically dragging the books to the photocopier, and was kind of impressed by photocopiers actually, because when I was at school we had spirit printers. We didn't have photocopiers, so this was like new technology. And I remember reading this thing and thinking, that'll never happen. And, you know, we've gone past it already, you know. So my walkie-talkie phone does this. And people talk into their phones like, what was the guy called? Some space-age detective used to do. So technology is amazing. I want to touch on this, and we're going to draw a line in a minute. Actually, I'm going to draw a line here. We've got 5 minutes. Let's just draw the line there. So let's have a look. We end on the last slide we do is 11. So L11 is where we end. L11 end. And let's have a look. Where did we start? Circular motion. So let me just flip back to that. This is going to be a bit messy, but we'll do it. I'm going to lose it. So let's flip back to there. And rotation. Sorry, circular motion. Second section. So boom, 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 boom. That's right, wasn't it? Yes. So H9 to H9 to L, was it H? L, yeah, L11. So those. I need to take a picture of that because I go home. Although I'm going to write your test soon, I go home and I just can't remember it. So it is, for those people at home, it's H9 to L11.